Thank you, Oscar. I'm Manjunath Korantla. I'm an architect at NVIDIA, and this is one of the efforts that I'm working on. And we have many active participants, and we'll be talking today in this hour. What I'm going to do is I'll give you an overview of UCC, what this project is about, and where we are today. So uh, jumping ahead, right? UCC is Unified Collective Communication. It's an open source project. It's an effort to create an API and library implementation of collectives. It is a project under UCF. And I've spoken about this project last year. And what I'll do today is I will give a kind of if you have listened to my last year's talk, right? The first part of the talk will be kind of a refresher on what we did and how we are doing that. And then I will talk very briefly about roadmap as well. Um, it's rather very short update. And I'll also talk about API and the design. After that, Valentin will talk about how we are implementing hierarchical collectives in UCC. Then Sergey will talk about GPU collectives in UCC, and then Farrell will talk about how we are supporting RMA-based collectives. So let me go talk about the design. So as I mentioned in the first slide, our goal here is here to create a collective stack, a single unified collective stack for HPC and GL and ML workloads, but particularly our focus is on collective operations and the group operation. So this is one of the design goals. As a result of this goal is challenge to support a wide variety of semantics because to serve both HPC and ML and so forth, right? And then also we want to optimize for different sensitivities. For example, deep learning would benefit with bandwidth optimized collectives much more. So we want to have collectives that is optimized for latency, bandwidth, and so forth. And also if you think about DL workloads, the ordering expectations from collectives is a little bit different than HPC. So when we decide to have as a goal of supporting HPC and DL and ML, we need to think about all these semantic challenges. So under any going to next point, right? Any stack you build today, right, especially the collectives operations, you need to support both the software and the hardware-based transport. What I mean by that is, say that one typical way to build collective operations is to build on top of point-to-point operations like UCX, and another way is to do on top of hardware transport like SHA. So it makes sense to support a single collective stack for both of these transports. Once you keep this as a design goal, right, then you need to think about resource exhaustion, especially if you have hardware transports. Resource exhaustion should be handled much more gracefully, right? And then we need to have fine-grained control over some of the semantic like reliability. So we had to address these challenges. And also for this stack, it makes sense like to support overlap. What I mean by that is to support while the collective is progressed, so that computation can progress as well. Then we want to support parallelism. What I mean by that is we want to progress many independent collectives. And another one we want to unify is we wanted to provide a single stack for collectives for CPU, GPU, and DPU. So to understand this, let me explain. The execution models that can abstract two different execution. Let me explain two execution models abstractions, and we think these two are enough to map to collectives for CPU, GPU, and GPU. Are you guys still with me?
Yes.
Okay. So like in the two-way, I just lost the power, so I just want to make sure that you guys are still with me. So two-way execution model, right? In this, the thread that is calling the collective, the thread that's executing the collective, has a little bit less overhead. So in this, what happens is you can go and call the execution thread and understand the progress, return values, and so forth, and you pay less cost. And if you think about this kind of a model maps well to something like CPU. And another model you can think about what we call a one-way execution model. Uh, Here, the thread calling the collective and thread calling the executing the collective, to interact between these two, right, there is a higher latency. And if you think about this kind of a model maps to something like GPU and DPU. So we kind of want to support these two models and map these to either CPU, GPU, and DPU. And we think this can cover a lot of variety of architectures. So with some of the design goals set and understanding the semantics, right? We wanted to define how the solution should look like. There's a lot of solutions that can solve, right? Like, but we wanted to define the properties of the solution and then define the solution itself. So one of the properties is scalability of performance. I mean, this is very obvious. You need to provide these two in any solution, particularly for common use cases. As I mentioned, we want to keep our solution extensible because we cannot possibly cover all the options and features, right? Especially if we are trying to unify a stack for many diverse workloads. And the third point, opt-in and opt-out, is somewhat is a way for customization, right? Say you are on HPC you are a HPC workload. You want to customize your stack in a certain way. And any solution we design should have this property of opting to a certain solution and opting out of certain solution. And we strive very hard to make the semantics as explicit as possible. And whenever we can, we move away from implicit to explicit. So with all these properties, another competing properties, still keeping the APIs small, fairly small. It's just because it helps to program with UCC. And so we are hoping that UCC hits many of these points. So our solution basically we can think about like about three important concepts. It's abstractions. Here abstractions that basically abstract the resources required for collective operations. Some of the examples are low abstraction that's local, or library, context, endpoints, and execution engine. And I will go in a bit more detail about this, so you will understand. Then there's a global abstraction, which is teams. And again, I'll go talk about this in detail, then it makes sense. So once we define the abstractions, right, the way to interact with these abstractions is operations. So this is another concept that ties abstractions, and then we'll come about how we do customizing these abstractions. So you can think about typical abstract operations on the abstractions as create, modify, destroy, and in case of collective, it's build, launch, and finalize. So as I mentioned, right, we wanted to provide a way to customize many of the semantics. And the way we achieve this is through properties. This provides a way to customize both the abstraction and the operations. Again, as I go through some of these abstractions, right, you will see the examples. So we wanted to define properties that is on a single abstraction, like library context, or which is sometimes cross-cutting. And you can think about it, right? This is a way for user to express the preferences to the library so that library can maybe customize the resources or semantics and provide what the user wants. You can think about this is a two-way interaction between a library and the user. So obviously, I will not be able to go into all the details. The best way is either going through the code or slides. But in the rest of slides, I'll try to give a brief overview of the abstractions and API. So let's jump ahead to the abstraction collective library. You can think about the collective library is as an object to encapsulate all the resources required for the collective operation. Um, so well, you cannot, I mean, one of the semantic is, right, you cannot do any UCC operations before creating a library object and after destroying the library object. So obviously, as I mentioned, one of the focus is customization. We provide various opportunities to customize it. And who is the user of this library is either a programming models, or I think we believe our API and abstractions are rich and simple enough so the applications can use directly. Some of the operations on this library would be initializing and finalizing the library itself. So let me show you the C interface. This is a screen grab from the header file. So if you are using UCC, this is one of the first operation you want to use is to create the object library object. The params and config is a way to customize the library. Let me go over it. So as I mentioned, right, we have three important concepts here: abstractions, operations, and the properties. Uh, you can think about this as the properties. So mask here, which is the first field, tells which of these fields are valid. The thread mode tells what is the thread model that user would like. I'll talk about it in next slide. And the call types, basically the user can express what calls collective types one expects, the user expects, so that library can provide those. And reduction types is exactly similar, like what reduction type, like for example, whether user would like say some, prod, and max or something, right? And as you remember, if you go back to this slide, this is an input parameter, and the library's library object is output, right? User is providing an input on what the user expects, and library object is built around that. And the way to query these properties of the object is through a query function. We have a query function. And so then there is a sync type, which defines a synchronous model. We support two models. Actually, we support we define two models, the synchronous model and asynchronous model. For now, I will not go into detail because I've gone through that multiple times. But if somebody wants it, I can. And the reduction wrapper is a way to call the user-defined reductions. However, we are debating to remove this and simplify this furthermore. So thread mode, right? Which support three different thread modes, single, funneled, and multiple. So user should use single mode when user application has only single thread. And the user should use funnel mode when user can has multiple threads and only one thread is calling the UCC library. And UCC thread multiple, user should use thread multiple when the user expects the user calls the collectives in multiple UCC in multiple threads. If you think about this, this maps to MPI model and MPI model and the OpenSHMEM model almost one-to-one. And the main users of these thread modes are MPI and SHMEM. So then the next abstraction is a communication context. You can think about this as an encapsulation of a local resource. Typically, you want to map context to network parallelism. Say you have an HCA and it has multiple uh, parallel engines to progress the communication. You want to express this with context. Um, this is an interface to create a context. And as I mentioned, the context can be an injection queue or something like a network parallelism. You might want to couple context with threads, process, or tasks. And you can have a single MPI process can have multiple contexts, or single thread can be coupled with multiple contexts. These are all valid semantics. Again, like you can express affinity using context. And we also can use the context to resource sharing. And think about this, right? Like if you have a HCA and if you have it provides certain level of parallelism, and you expressing context using that, you can provide multiple context to a collective or a single context. This will help with both the performance and if you run out of resources with resource sharing. And also you can build collectives such that each a context can be a software context and a hardware context, and you can combine this into a team. So currently we don't support all the options, but eventually we're going to support. So just showing the C interface to create context. UCC context create. It takes in a library handle and again parameters and config. As I mentioned, this is a way to customize the context, and the output is the context. So one of the properties that we have on the context is to express how it is shared. We have two types of context. One is exclusive and shared. When a user want to create an exclusive context, when user wants to map this to a single team. When the user says it's creating a exclusive context, the library is now free to do a lock-free implementation. Um, and in case of course, the user can do a shared context. In this case, typically you are sharing the context with multiple teams. In this case, the library might have to protect some critical sections. So next, jumping into another abstraction, teams. Now, what we did was we have a library and the context. Now we are creating a team. If you are coming from MPI world, right, you can think about team as a MPI communicator. So essentially, it is providing a way to encapsulate resources for communication operations. It is created by UCC team create post. Um, it doesn't really require explicit synchronization, but there is a communication between all the all the participants of the team. So it's a non-blocking call. However, only one operation can be active at a time. So let me see if I have, yeah, let's go, if you look at the interface, right? We finished building a library object. From the library object, we build the context. From the context, we are building the team. You can pass single or multiple contexts, and we have team parents. Again, this is a way to express customizations, and you create a team. So there is lots of customizations here for team. So mask here says that which of these fields are valid. For example, ordering, which says that how the collectives are called. So there is an ordered and unordered model if you're coming from an MPI world, right? Or for a given communicator, all the collectives are called in order. So that is how you express here, but it's not necessary for all programming models. Outstanding calls here says that user makes certain kind of promise saying that there can only be so many outstanding collectives. This helps library to manage the resources. And the endpoint, you can think about from a collective perspective. This is as a endpoint of the collective. Again, if we map this to MPI world, you can think this is nothing but a rank. EP list, we can give endpoint and a list of endpoints who are participants of the collective. Let me skip EP range, but actually I can say EP range it basically says that whether these endpoints are contiguous or non-contiguous. And team size again is obvious. Sync type is very similar to what synchronization model that I was talking about in library. The values can be either synchronous or asynchronous. So we provide multiple customizations. We can define the synchronous model on the team or on the library. OOB. So typically when you want to wire up the team, you need a way to communicate. And if you are working in a programming model, another programming model, right? Typically there is a way to communicate, and we want to leverage that to build a collective team. And the P2P connection provides a way to map share resources between point-to-point and collectives library. And memory parameters, basically we can attach some memory, and typically attaching certain memory and doing collective on that memory, right, can really map very well to some PGAS kind of collectives. Farrell will go in touch upon this and show you how we use this in PGAS collectives. EP map here provides it's a way to map the context to the team. And again, team ID here is a unique integer identifying the team among the active teams. So with that, we'll jump to collective operations. Collective operations. So we have a team, context, and library built. So once we have this, right, we can initialize a collective. So when you call the collective in it, you are building all the resources or initialization and required for the collective. And when you are ready to post a collective, when you want to really do a collective operation, when the data is ready, you want to call a post. If you want, in some of the models, collective models, you might want to merge this. So init and post is more of a convenience wrapper. And once you finalize, you cannot call the post again. So here we release all the resources. So with this, right, let's see how we support different collective models. I can skip this and let me go here. Say if you want to build a blocking collective, right, we can implement using the building blocks. For example, init and post plus test and finalize will give blocking collective semantics. For example, you want to implement persistent collectives, right? You can do init and just do post and test for every time you want to call a collective, and you finalize only once. You don't need to call this collective again. Split phase collective is almost similar to non-block collective, except there is a promise that there's only one outstanding collective at a time. So we can support various collective semantics in a way with these basic building blocks. So another new abstraction or we introduce over this year is triggered operations. So in a way, I kind of made an assumption that the collectives are executed somewhere, like either a CPU thread, right? Typically a CPU thread. I just made assumption it's executed there. Um, it's okay to make that assumption when you have executing the collective lay or say always on a CPU thread. But with the current architectures where we have GPUs, and CPUs, right? Uh, it's actually better, in our opinion, to bring out this execution context where the collective is executed. One is because typically when you consider all these architectures, right, CPU, DPU, and GPU, the execution context properties are different. The underlying architecture is different. And in case of, say, DPU and GPU, right, the thread that's calling the collective, the thread that's executing the collective might be different, right? So having an explicit abstraction, we feel it's helpful. And this abstraction we call execution engine. And on this execution engine, we do event-driven execution. So again, if I go back to our post example right here, I just made an assumption when UCC collective post is called, the collective executes right away. But with supporting various diverse architectures, right, like CUDA streams or CPU threads and TPU threads, we don't want to make that assumption because there is a bit of asynchrony, right, from the calling thread and the execution thread. So we wanted to support event-driven execution. So we have event-based execution on the execution engine. The execution can happen on library generated events, like a completion of operation on launch of collective, or user generated events like compute complete and data ready, right? In a way, tying all the execution engine and the events is a triggered operation, right? This is an extension of, you can think about this as an extension of the post here, where instead of post, the collective executing right away, it executes on a certain event. That is a trigger. So we provide a way to define a team, whether the team does the triggered operations or not. So when you are building the team, right, you can say that, okay, I want a triggered operation or not, right? So um, this is kind of a cartoon showing how this happens, how a user thread generates the events and how the library executes it. I will not go into this because Sergey later will talk about this in the context of GPU collectives. Then it will be much more concrete. So with that, right, this is really like a very brief overview about the various concepts. Obviously, it's not detailed, right? There's a lot more details in our specification. If you are interested into dig deep, right, please go read. It's available publicly. And then jumping to implementation, right? This is the component diagram reflecting how our code is organized in a way. So again, I'll try to go very briefly. So on the bottom, these are the transports. We support today UCX transport, nickel transport, and hardware sharp collectives transport. So abstracting this transport is in the UCC code is UCP-TL, nickel TL, sharp TL. We don't have a shared memory TL and yet, and proprietary TL is a way to say that certain vendors want to use the infrastructure, but not necessarily show some of the proprietary parts of the protocol, right? They could plug in their transport here. On top of that, is a CL, collective layer. The collective layer, you can think about various strategies to implement the collectives. I mean, in the basic, right, it's almost a very close mapping to the TL down, except the composition part. Hierarchical CL is another way to implement collectives, and Val will go into details here. Say that somebody wants to use all this infrastructure, right, but want to have their own collective strategy, not necessarily expose it. There is an opportunity to plug in. The core component implements most of the APIs, and the internal API reflects or is very close to the external API. So here I'm showing how the programming models can use, right? So as I mentioned, the UCC API rich enough and also simple enough for the applications to use it. Our OpenMPI, today we have integration with OpenMPI, SHMEM, and PyTorch. Of course, we think one can integrate it to task-based programming models, or MP2 can use it, for example. So this is basically showing that we are a very active project, and there's a lot of updates. So this is just again showing that today, what are the integrations we have done. We have integration with OpenMPI. It's available for 4.1 and above. We have support for OpenSHMEM 1.4, and we have support for PyTorch, and via third-party plugin here. So releases. So we did a release earlier this year with support for collectives for MPI, and also I think PyTorch as well. We supported many algorithms and data sizes and system configuration. We had support for CPU and GPU collectives. We supported basic data types, and we had a testing infrastructure. So we are expecting to make another release very soon. In this release, we had support for Sharp. We had supported for optimized collectives, that is hierarchical collectives, and we had support for OpenSHMEM. We had support for nickel collectives. And of course, we are currently discussing how to support support some generic data types beyond basic data types. So with that, that's my last slide. And as I mentioned, this is an open project. We welcome all the contributions. There is multiple ways to engage with us, either participating in weekly working group meeting, or on the GitHub. We have a Slack channel, and on the mailing list. And of course, we welcome contributions to design, documentation, code, testing infrastructure, code reviews, anything. There's a lot of work, and we're happy to take your help. So with that, I'll take a pause, and after that, I will hand over to Val. We'll talk about hierarchical collectives.
So should I reshare the screen, or you will?
Please go ahead and reshare. I'll stop.
When are the questions? Like in the end of the whole talk, or are you going?
Let's take one pause and see that if there is any high-level questions. So.
Yeah. Any high-level questions? Okay. I have one, but it's very quick question.
Sure, Oscar.
Is there any thoughts about user-defined collectives? Like a user wanted to have basically a new operation or type of collectives, or implement a new algorithm and so on, to be able to have an API to help in that direction, like instead of doing preloading, library preloading or something like that.
No, I think I'm not really sure we need that API level support. Maybe I need more details right before doing it. But I think one nice way is writing a CL is relatively straightforward. If you want an algorithm to be implemented right, you can implement, you can define a new CL and write it there. Or if you think that you just need a new algorithm, right? Writing a new TL is a better way. Yeah. So could user provide pointers to serialization routines? Can you please refer to what you mean by serialization routines here?
Yeah. Hi, sorry about that. So if I had like a user-defined data type and I wanted to do some kind of collective operation with it, would it be possible to like pass you pointers to marshalling and unmarshalling routines, like a function?
I see. I see.
And that just handled that for you.
Yeah. So today, actually, we are discussing this,
maybe bind that to a context or something similar.
So we want to support that. It's not integrated, but we are currently discussing that. There is one PR that we are doing that today. Yes, our plan is to support that.
I mean, it is merged, in fact.
Oh, it's merged. Okay. Okay. It'll be. We'll have support.
So it's done similarly to the UCP so far, like, and the data structure that describes the data type is exactly the same. Like you have the predefined types and then the generic data types with the streaming, like pack and pack callbacks. And you can also define like custom reduction on top of custom data type.
So does that answer your question? Yeah.
By the way,
yeah, everything's great. Thank you.
By the way, small comment about the similarity to UCP data structures. I noticed that in your parameter structures, you don't have bit fields. And in the future, if you would want to extend this parameter structure, it would be very hard to maintain backward compatibility.
I thought we added, I mean, let us check.
At least on the slides, I did not see a bit field.
Well, and I don't think that the slides are actually like up to date.
Totally.
Okay.
Like,
Okay.
But we will double check that.
Yeah.
So should I start?
Please go ahead, Val.
Yeah, so I will basically talk about one piece of the UCC library, which is hierarchical collectives. And so the term that is used, so it's not new thing, it's like commonly used technique to implement collectives. And in this scope, what I mean by hierarchical collectives is the way to implement algorithms when you split the group of processes, the original one, the communicator, into subgroups, and then you can represent or express your collective in terms of smaller collectives launched on those subgroups. And this was done many times in different frameworks in Monox, HCO library, and OpenMPI. There is implementation right now. So, and here I will just briefly touch upon how we do that in the UCC. And this type of collectives, sometimes you can write an algorithm latency oriented, and you can write some other algorithms like for best bandwidth as well using hierarchies. I will give a couple of examples of those. So I meant I mentioned subgrouping, saying that first we split the communicator or the group of processes into the subgroups. So here's just an example of what subgrouping is like. Let's say you have several nodes and the job is being launched, and there are, let's say, we launch 4 processes per socket. And each node has 2 sockets, so it's 24 processes. And then the subgrouping is basically partitioning of those processes into groups based on some features. For example, based on the locality. If all processes are on the same socket, if they bound to a socket, then they will form one group. You see 6 such subgroups here. Then we can take one process from each subgroup and then put them together on a node and call that group of socket leaders. each one of them represents the socket. Then you can take another one process from each of those groups, and they will form yet another group of node leaders. And so when you can like put them that way, you see they form the hierarchy. Now you can use it to implement some algorithms. Here's an example, the O-reduce, 5 steps O-reduce that you would like standard thing, the way you do the O-reduce over the such hierarchy. Like you start with the reduce operation inside the socket subgroup. After that step, socket leaders has the local reduction. So then they do the reduce in the group of 2, and then the node leaders do the O-reduce on top. After that step, each node leader basically has the answer, the total result of the O-reduce, and they just need to broadcast it down the hierarchy. So first the broadcast goes in the socket leader subgroup, and then within the group of socket. So for the node leaders process, it will be 5 steps. For the gray processes here that are like leaves in the tree, it will be just 2 steps, reduce and broadcast within the socket. So this is an example. This kind of O-reduce would be best for the for latency. And another advantage when you do such thing is that you can actually use different transports on different levels of that hierarchy. Like between node leaders, you need to run O-reduce, and there you can use, for example, sharp if it's available. And yeah. So by the way, I will probably go back. So Maju showed the diagram. Let me actually spend some time here. Maju was quick there. So in this diagram, which shows our architecture, we have that, I mean, the core layer, which, as Maju mentioned, implements our main API that the application interacts with. Say here we create a UCC team, which maps to OpenAPI communicator. Then the team itself in the core, it will create potentially several CL teams. So CL is that upper layer where we, it has high level implementation of collectives using different TLs. So now what is TL? TL is actually like collective transport layer backend that implements the interface. And the interface itself is also like collective primitives. For example, in UCPTL, there is an implementation of reduce, broadcast, barrier, and other stuff, and similarly in other TLs. And then when we build hierarchy, we can use these TLs as pieces, as the steps in the different levels of hierarchy, right? Like here, reduce, it can be called from different TLs of each step. So another example of hierarchical O-reduce now optimized for bandwidth. So the picture is actually taken from other talk, but bottom line, let's say we have several nodes and we want to perform the GPU O-reduce over GPU buffers. So if we have, say, 8 GPUs per node and we have rail, and like each GPU in this example has its own HCA, so we kind of have 8 independent rails. Here's then one of the approaches that you could use. You can discover subgroups. First group would be all the processes on the same node. So the size of that group would be 8. And then another group would contain processes on the same rail, like across the nodes. And then the O-reduce would be 3 steps. First, you run reduce scatter within the node. After that step, each process has 1/8 of local reduction. Then you launch like 8 parallel O-reduces on each rail. And then after that, you do the all gather. So you collect back and then you have the final answer. And then you can, so this is 3 steps, then you can pipeline them, like fragment the O-reduce, pipeline, and have the overlap of in-node reduce scatter and inter-node O-reduce. And then like you could potentially reach full bandwidth that way. So that's another example that hierarchical algorithm can be used for bandwidth optimization. And in UCC, so as I mentioned, what we need to do, we need 2 pieces. We need a subgrouping framework, and then we need a way to express these collectives in terms of TL primitives. So to do the subgrouping, we have Topo, it's called Topo, the small framework right now inside UCC. What it does, it allows discovering of those subgroups. To do that, each process during init collects some local information, like host hash, ID of the socket, or NUMA domain if it's bound to any of those. And this is embedded into the context address. Then the context addresses, they exchanged either during context creation or during team creation. It's not important right now, but after all, each process has those addresses, and you can extract process info and build the structure that contains sorted array of those process descriptors. After that, all that subgrouping is totally like local routine, which is done basically, it's fast local routine. And we initialize that struct on demand when some TL or CL reports that top is going to be used, because like CL basic, for example, doesn't use any subgrouping, so it will not report that top is required. If user enables CL hierarchical, then this additional step will be done. And so CL hierarchical is the collective layer on the diagram that implements hierarchical collectives. In contrast to CL basic, for example, CL basic just selects which TL to use. Let's say you run UCC, you compiled UCC with Sharp support, UCP support, and you run CL basic. Then CL basic can select based on score of TL, where, for example, we will launch a collective. If user launches all reduce and Sharp is available and UCP is available, then Sharp will have higher score based on like latency, bandwidth estimations. So CL basic will direct the collective to Sharp. CL hierarchical does more than that. So it will actually implement hierarchies, it will discover subgroups, build a sequence of steps that are needed to express the collective, and it will run it. So here is a little bit of like additional information, how we actually express the collectives. And to do that in UCC, there are two main like structures. One is task, UCC call task, another one is schedule. So the task is it's like minimum amount of work that TL does. So the task represents like a collective operation over TL. And in TL, in UCC, we have a common interface so that TL can initialize and give the task up to the colon like CL or core level. When task is initialized, it gets the collective arguments descriptor, very similar to what we have in core UCC API. So it has the collective data type, pointers, sizes, and all that stuff. So it's passed down to the TL, and TL initializes the task and gives it up to the core level. Then it can be executed. The key, another part of the task is what is called event manager. So this is a simple entity that allows delivering events between tasks. So to the right, you can see like there is a call event manager subscribe that allows one task to subscribe and start to listen to the events of another task. So already with that, if one task subscribes to another one, then, for example, if there is event completed, generated on the first task, then there is a specified callback triggered for the second task, and second task can do something with that. For example, it can be started itself. So now we have a sequence of tasks that way. And the third thing here is called a schedule, which is basic. It's also a task, and it is a collection of other tasks. So I'm giving here a simple example how right now CL hierarchical implements that two-level all reduce. So this is a simplified like pseudocode, but basically the idea is when user, MPI calls a UCC collective init and passes the descriptor of the all reduce operation down to UCC. So this call collective init goes to core level first. In the core level, we have two CLs, basic and hierarchical. If hierarchical gets selected, This depends on the scoring and other stuff. But basically, if CL hierarchical is selected, then we go to this function, which initializes the schedule for the hierarchical collectives. And basically, it will be 3 steps. So CL hierarchical at this moment already discovered subgroups. So it has the subgroup of node processes, so all the processes on my node. And then second subgroup is the group of node leaders. And at each subgroup, we initialized TL teams. So they basically like a sub-communicators of the original communicator, but at TL level. At each subgroup, there can be several TLs, and again, they will be, the best will be selected based on the scoring interface. Now we need to allocate 3 tasks. Basically, the first task is reduce within the node. The second task is the all reduce, and third task is broadcast. Once we allocated them, we want the first task, task 0, to subscribe to the event started of the schedule. And then each second task subscribes to event completed of the previous task. And then all tasks are also being added to the schedule, because schedule is actually the object which inherits from the collective request which we give up to the user, to the OpenAPI. So OpenAPI will test the completion of schedule. And since schedule knows all its tasks, it can track the overall progress. So that's basically how hierarchical algorithms are expressed and implemented in UCC. And so last slide, just giving just an example how to interact with CL hierarchical. And again, like this, the parameter to the right, the long one, like CL hierarchical node leaders SBGPTL. So this is the long name which user can specify. Okay, I want to use several different TLs at the top level of hierarchy in CL hierarchical, right? So there is a node leader subgroup, and I can potentially list several TLs to be used there. And then depending on the the score they report, depending on the availability, CL will select what is the best to use on the top of the hierarchy. And the schedule itself is kept the same. Only TL backends change at different steps. So that's pretty much it, how the hierarchical collectives are implemented. If there are any questions, I can answer. If no, we can go on.
Yes, I have a question. Do you have some sort of fast path for the latency critical collectives? Like you showed a value of all reduce running with 4 bytes, but with quite big scale. And I think if it would be much less scale, the overhead brought by this hierarchical infrastructure, I think maybe could be too significant, right?
Yeah, so that depends. Like right now, so the short path in this case is going to CL Basic and running like some TL directly. Like if you would run 2 processes on the same node, like this is the minimal scale, like the opposite. So then the best would be to go to CL Basic, which directly, I mean, the collective init would give you the task object from like TL SHM that we're implementing right now. And then on the task itself, there is already a pointer to start the collective. Like this is the shortest path. And the thing is that, right, so the way it is done, we have a selection logic that gives a scoring to all those different CLs and TLs, and CL hierarchical will get selected at some scale. Depending on like how many cores on the node, how many is like, how deep is that hierarchy, how many sockets, how many cores on the node. It can be like the scale that where you have the benefit from going over hierarchy can be already like 2 nodes, really. Like if you run it vice versa, you run just PPN1, like 1 process per node, of course, we will just not enable hierarchy at all. So answering your question, like there is a way basically the fast path is the path to CL Basic, and there is a way to select between those. What we don't have right now, we don't have the automatic way. Like we don't have basically we don't have the tunings right now at all in UCC. That's like the piece we will be working somewhere like soon. So we don't have the tuning and selection, like we don't have default settings, like where is the cutoff to go to hierarchy, where is the cutoff to go to CL basic. But there is a way in the interface that allows you to go like directly to TL.
So
to
it-
add to what Nihal, to add to what Val is saying, right? I mean, in a way, we also think about latency differently in collectives, right?
Yeah,
we are
sure.
not
Latency.
looking at we are not looking at two nodes and say that we want to optimize for two node or two process latency, right? We are looking at the scale. We are okay to pay a little bit of latency to achieve scalability, right?
Okay. Yes, but two nodes is just an example. Another example which Valentin mentioned is better, I think, when you have just one
Yes.
process per node. So you may have quite big
Correct.
scale.
And hierarchy will not be selected for that night.
Yeah,
Yeah, sure. And even like two process per like one per socket. I mean, there are cases. I mean, we have a way to I mean, basically to not to hierarchy in that case, and you can express it in different ways. What we don't have like right now that already those rules and like the logic to do that. Right now, like even cell hierarchical right now by default is just disabled. So you would need to enable it explicitly. That's the state of the like UCC master branch right now. So we will need to do the work of making defaults.
But eventually it's supposed to be done automatically, and all this selection will be transparent for the user, right?
Of course.
Okay, but currently user has to decide what CL to
Yeah, if
use.
user does nothing, it will just run like basic. CL
Okay.
basic. In CL basic, there is like some, yeah, but basically the answer is yes. Right now, user would need to set some parameters.
Okay, thanks.
Probably we'll go to GPU collectives from Sergey, and then at the end we can touch back if we have any other questions, right?
Okay, can I start sharing the screen?
You can or you can't?
I'm asking.
Yeah, I'm stopped. Okay, so it's yours.
Okay. Can you see it?
Yes, we can.
Okay. So I will talk about the GPU collectives. Oh, by the way, I'm Sergey Lebdev. I'm working at NVIDIA on collectives library and also application for and deep learning workloads. So when talking about GPU collectives, it is important to distinguish between two topics. First of all, support for GPU memory, and what I mean by that is when source or destination buffer allocated on GPU. So it can be CUDA managed memory, CUDA regular CUDA memory, but something different from host memory. For collective library, it's also important to have support for different GPU-specific data types like float 16 and bfloat 16. Of course, they're used on CPU in CPU world as well, but they're more widely used in GPU tasks. And finally, we also need the support for reduction operations by using GPU kernels for reduce scatter or all reduce collectives. The second topic is how collective library interacts with GPU programming model, because GPU programming is something different from CPU programming, and there are some concepts that collective library should be aware of to do the job efficiently. So I will start first with the GPU memory support and then go to the second topic. GPU memory support is a well-known topic, and it is implemented in many libraries and frameworks. And for example, UCX supports it for a long time already. So in UCC, we have a way to let users specify the memory type of the input or output buffer by setting the corresponding field in the call buffer infrastructure. So the possible values for this field is memory type Cuda, memory type host. And also the one choice is UCC memory type unknown. This is needed to support some programming frameworks like MPI, where user cannot specify the memory type directly. So if user sets memory type unknown, then in that case, UCC will try to do the best to detect memory type itself. Then once we know the memory type, collective operation is passed to one of CL or TL, and that supports GPU memory. And each TL tells the core function what memory types it supports. Then the score function select the one with the biggest score. Also, each TL can use the UCC memory components. UCC memory component is a set of predefined operations. I will show it in the next slide. And finally, I want to say that for release UCC 1.0, all the TLs supports CUDA memory. We have TL UCP, and it supports CUDA memory because UCX supports it. TL Sharp and TL Nickel also supports CUDA memory. So UCC memory component is the base interface, and each memory component implements all these functions. Some of them are memquery to give some memory attributes for the pointer. For example, for CUDA memory, it can be the base address to know the base address allocation of the memory. Also, each memory component implements alloc and free function to do memory allocation. And this is the responsibility of each memory component to do it efficiently. Of course, it can be implemented like calls to malloc and free, but the more efficient implementation is to use some sort of allocators. And also, memory components is responsible to do reduce operation. So this reduce callback is different kind of for different memory components. For example, for CPU memory component, reduce is nothing but a simple host function. But for GPU memory, for CUDA memory component, reduce is a GPU kernel. And this GPU kernel is optimized to do reduced operation on one or multiple buffers for different reduction operations. All these components are loaded in runtime, so we do not have any dependency. I mean, we can load them on demand. So supporting for memory type, for GPU memory type is a well-known problem, but the more interesting thing is how to support CUDA programming model and how we can do it from the collective library perspective. Briefly about CUDA programming. In CUDA, we write some functions called kernel. Then we start those kernels from host. And important thing to know is that kernel is executed asynchronously with respect to the host thread that starts it. It means that if user wants to get the result of kernel, it needs to call some sort of synchronization routine like CUDA device synchronize. But if user will do that too much, I mean, calling synchronize each time, it will be very inefficient in practice. That's why in Cuda there is a notion of stream. The stream is something like a software-defined queue. So different kernels can be submitted to different streams, and two rules applies to stream. Those two rules, operation submitted to the same stream will execute in order, which means that if I issue kernel 1, then kernel 2, then kernel 2 starts only when kernel 1 is finished. And the second rule is that there is no guarantee about execution order of kernels in multiple streams. They can execute concurrently, they can run sequentially. It's up to GPU to decide what to do. And what we can notice is that collective operation can be considered as the Cuda operation. And from that perspective, it also should follow stream semantics. Here, the simple example that demonstrates, I have two kernels here, compute kernel 1 and compute kernel 2, and I have a collective operation in between them. So what happens is kernel 1 produces the compute output buffer, then we start all reduce operation, and then kernel 2 computes something based on the all reduce. But if we do it this way, there is, of course, a problem of data races. In particular, we have a race here, meaning that when we start a collective operation, when we start all reduce, the data in compute output buff might not be ready. So kernel may be still in progress, but we start a collective. And the second race is here. When we start a second compute kernel, maybe collective operation is still in progress because kernel 2 starts once kernel 1 is completed. It doesn't know anything about collective operation. So we call this input dependency and output dependency. And the solution to this problem from UCC API perspective is to use triggered operations. The triggered operations, what Manju described, introduced two new concepts. First is UCC execution engine. And in case of Cuda, it directly maps to Cuda stream. So UCC execution engine is nothing but a Cuda stream. And then the second thing is UCC collective triggered post. This operation will do the stream in queue, or it will issue the collective operation into stream. So this is the modified version of the previous code, but now it uses triggered operation semantic from UCC. What has changed is we create a UCC execution engine here, setting the execution engine type to Cuda stream, and also providing a stream. So we need one execution engine per stream. Then we start compute kernel 1 on a stream here. Then do collective init as usual. There is no something special about GPU or streams here. But we change UCC collective post to UCC collective triggered post. And now we specify that we want to start this collective once this event is generated, when this kernel completes. And after that, we start a second kernel. In this code, there is no data races. So UCC will guarantee that collective operation will start when kernel 1 is finished, and kernel 2 will start when collective operation is finished. From the TL perspective, each TL implements triggered operations differently. For example, TL Nickel, we have nothing to do. TL Nickel natively supports Cuda streams, and this is very obvious. But for TL UCP and TL Sharp, we need to implement some additional logic. And the main points are, we need to satisfy input and output dependency. but this is quite obvious. But not, what is not obvious is that we need to issue all Cuda work to stream before return from collective triggered post. This is a long topic. I will not touch it, but this is something related to Cuda programming. So how it looks, first we start a Cuda kernel. It occupies a stream. So we have a Cuda kernel here. Then we do UCC collective init. It creates a UCC collective task. And then we do triggered post. Trigger post enqueues a trigger task to stream. And then UCC collective task subscribes to event from UCC trigger task. Once UCC trigger task generates trigger complete, UCC collective task starts all reduce. At this time, UCC trigger task waits for notification from collective task that will say that all reduce is finished. And then when it gets this notification, UCC trigger task ends and next Cuda work can be executed. So this is the basic diagram. There are different implementation for UCC trigger task. The most the obvious one is to use a UCC, a wait kernel. And the wait kernel is a tiny Cuda kernel that occupies stream. It does not consume a lot of computational resources. But also we support marking the stream busy with some driver API if it is enabled. Again, if details can be found in UCC source code or documentation. For the future work, I want to mention that we want to implement a new TL called UCC TL Cuda, and this TL will work on a team that spawns the one node, so all ranks are reachable through NVLink. This TL will be GPU topology where it will know about the NV switch or hypercube mesh topology. And it will also support all reduce and reduce operations natively for triggered post. Again, details in this pull request, it's still in discussion. So if you have any ideas or feedback, then welcome to contact us. Yeah, I think that's it.
I guess I'll go ahead and switch, or are there any questions on that?
Please go ahead because of time.
Yeah. Okay. So I'll try to be quick, so I'm not running over Jeff Watt's time. So we added in support for, or it's still in pull requests phase right now. It's not in master yet, but UCC one-sided RMA collectives. So the UCC or the one-sided collectives are just collectives that leverage one-sided RMA or AMO operations to perform collectives over a UCC team. And this gives us the ability to, or allows for loose synchronization on collective start and completion, taking advantage of those one-sided operations, and directly maps our point-to-point communication operations within a collective to the hardware primitives. And it's important that we provide this one-sided collectives so that we can provide support for PGAS programming models or clearer support for PGAS programming models, specifically OpenSHMEM, but including others as well, as they are already allocating and registering large areas of memory with the NIC at initialization time, and This allows for them to use RMA operations for point-to-point communication and RMA operations for collectives as well. In order to take the user pre-allocated memory that may be allocated by the user or a programming model and map that to UCC, we've extended the min-map params structures into two different structures where we have UCC min-map params T on the right, which is essentially like a IO vector of memory segments, where these memory segments could be something, say, for example, in OpenSHMEM, symmetric heap and global and data segments that form the memory model for OpenSHMEM. So they would be defined within UCC min-maps, which are just a base address and the length of those memory segments. And when the user passes this in, these segments can then be bound to a UCC context, which would allow that memory to be used by multiple UCC teams, assuming it's a shared UCC context. And the idea is that these one-side collectives would operate on these user-provided buffers for best performance. So an example of this, showing UCC context creation with the extended min-map params, with a context of this being similar to, say, OSHMEM. Actually, most of this code is from OSHMEM, pulling it out from there. So in this example, assume you have 3 memory segments, symmetric heap, global static variables, and maybe another segment for atomics, like we have in OSHMEM. So that would leave us with 3 memory maps. And from there, we just add in an additional parameter to the context param mask, which is UCC context param field min params to indicate that we have memory parameters. And then somewhere in here, we would maybe loop over our segments, assuming they have base addresses and links already predefined, which is typical for an OpenSHMEM implementation. We can just assign that to our UCC min map and then set up our min params segments and end segments to point to those maps and the number of maps that are there, and call UCC context create just like we normally would. So there's not much additional work there. During context create, there is the additional work in that you will re-register the memory with the NIC for memory that's already been registered by the programming model, for instance, which has some overhead, but it's not too significant. Beyond that, beyond creating a context, in order to call a one-sided algorithm, there's a few steps that need to be completed. The first is, because you're using a one-sided algorithm and you're only doing communication on one side, these collectives require some scratch synchronization buffer so that you can have clear completion semantics. There's 2 methods of allocating this. One method is to use a team-based buffer. It's allocated by UCC internally. The idea is essentially when you create a UCC team, it will go ahead and allocate space for these synchronization buffers, and it will be hidden from the user. The second method, which is actually listed as number 1, is that the user will allocate the buffer and then pass that in as an argument to the collective. And since there's a disconnect on how large that buffer should be, we've created a mask for context attributes so that we can actually let the user determine how big this buffer should be. So over here on the right, they can just set their attribute mask equal to UCC context attribute filled work buffer size. So our work buffer is this scratch synchronization buffer and scratch pad for the collectives. They can then get the attribute from the UCC context that's already been created and then allocate their local work buffer. So in OpenSHMEM, this would be like allocating your psync array. Afterwards, assuming they allocated these user buffers, like on the example on the right, during team creation, they just pass in UCC team flag call work buffer, which indicates that for all the collectives, they will be passing in their own allocated buffer. And then from there, they can call their collective at a later point without the team-based buffer being allocated by UCC. So there's a preliminary all-to-all algorithm, pull request number 323. You can go and look at it if you want. It's just a basic linear all-to-all algorithm that we've implemented as an example of this, which does something similar to this over here. So for every rank in the team, it'll perform a put and then an atomic increment on that work buffer, and a put on source and destination buffers, or put on the destination buffer from the source, sorry. Afterwards, it'll wait until completion, but you can see kind of how that might look internally from that pull request. Anyway, when you're going to actually call the one-sided algorithm, by default, we're keeping the one-sided algorithms disabled currently, I believe, because if you are trying to call a one-sided algorithm on a context that does not currently have memory allocated to it, your collective would fail. So just keeping that from happening by default. So here's how you would call UCC collective with the one-sided, say, all-to-all algorithm. So this is how you call that. The additional bits here are a mask to indicate that you have a global work buffer. This is assuming that you're allocated a user buffer. And this call args field flag to indicate that you have memory map buffers, which are the segments that you passed in earlier on context create. This allows UCC to know that all of your memory is already been registered with the NIC and registered with UCC context, so your collective should work appropriately. And you pass in a global work buffer, which is that work buffer that you allocated on the previous slide. Now, because the collectives are disabled by default, particularly the A2A algorithm, you can just use this environment variable, UCCTL, UCPTune, because these are all living within the UCPTL. For all-to-all, for data sizes 0 to infinity, use this algorithm, which is algorithm 1, which is the one-sided version. And that would allow you to use the one-sided all-to-all. But I think due to time, I'll end there. That's the last slide. So thank you. And if there's any questions, I guess, on anything, right, you can go ahead and ask.
Yes.
Yeah, please go ahead and ask questions for everybody on UCC.
Yes.
Sorry, Oscar.
Yes, and meanwhile we ask the questions, I will ask Geoffroy to start sharing his screen and presentation.
Okay.
So, any questions?